Can you see my desktop?
Yeah, we can see your presentation.
Yes. Okay. First of all, thank you very much for attending in this session. In this presentation, I try to introduce the concepts and the techniques about three, state-of-the-art AI technology. That means explainable AI, neurosymbolic AI, and also large language model alignment concepts, algorithms, and technology. So the crucial question is why we say, is there such a significant focus on trustworthy AI and machine learning right now? The answer is straightforward, okay? Because governments and major organizations are, demanding it. This isn't just about good practice, anymore. It's about fundamental requirements. First, they are, demanding transparency. Okay, we can no longer, treat complex AI system as black boxes. And we must be able to understand, and explain how, they make their decisions. Second, they require compliance, okay? As AI becomes more integrated into our society, it's essential, that these systems align with the growing number of the global AI, governance frameworks and regulation, and that are being established. This is precisely where trustworthy AI becomes essential. By adopting a trustworthy approach, we can proactively meet these complex, regulatory and ethical demands, which significantly reduces the risk of non-compliance and its associated penalties. As you can see from the graphic on the right, this is a global movement. Okay, we are seeing major interconnected and efforts in AI governance and explainability from key international players. This includes the comprehensive EU AI Act, the directive setting a White House executive initiative like order on AI and in the United States, okay, and the pioneering technological work from initiative like DARPA's Explainable AI program. To build on the idea of trustworthy AI, we need to talk about explainable reasoning. Okay, this is bring us to a fundamental distinction in AI systems, the difference between black box and a white box AI. Let's start with black box AI. As the name and the image suggest, the internal workings of these systems are opaque and complex. They might give you a highly accurate answer, but it's incredibly difficult. Okay, it's sometimes impossible to understand how or why they reach a specific decision. This lack of transparency can be a major roadblock to trust and accountability. On the other hand, we have white box AI. These systems are designed for transparency. They provide clear insight into how decisions are made, allowing user to see and understand the logic behind each conclusion. You can effectively look inside the box and see the gears turning. This transparency is why white box AI is so crucial for building trustworthy systems. It contributes in several key ways. First, it reveals each step in the decision-making process, which builds user trust and confidence. Second, every inference is traceable. Okay, this ensures accountability because you can follow the logic from input to output. Third, by exposing its logic, it makes it much easier to spot and fix hidden biases quickly. And finally, it achieves the holy grail of combining high accuracy with clear reasoning, perfectly aligning with the goals of explainable AI. In essence, moving from a black box to white box model is a critical, step in creating AI that is not only intelligent, but also understandable and accountable. So, sorry. So how do we achieve the kind of transparency we've been discussing? The answer is answer lies in the field of explainable AI. Explainable AI, or XAI, refers to a set of methods and techniques specifically designed to make the outcomes and internal workings of AI system transparent, interpretable, and understandable to us, actually the human users. As you might guess, this makes XAI a core and non-negotiable component of any trustworthy AI systems. However, explainability isn't a single tool. Okay, it's a collection of different approaches. These are often categorized based on when explanation is generated, okay, in relation to the AI model's operation. Let's look at three main categories, which you can see summarized in the table. First, we have Ante-hoc explanation. Okay, ante means before, and that's the key here. Okay, these models are designed to interpret to be somehow interpretable from the very beginning. Okay, think of simple models like decision trees or rule-based systems. Their strength is their built-in transparency, but their weakness is that they are often limited to simpler tasks. Next is in-hoc explanation. This approach is my favorite, approach and method in explainability, where in means during. Okay, this approach provides real-time insights during the model's decision-making process. If actually it focuses on process-oriented reasoning. Okay, this the major strength here is the ability to get real-time, faithful insights into the model's thinking. However, this can come with high computational costs. Finally, we have the post-hoc explanation. Post means after. These techniques are applied after a model, typically a complex black box, has already made its prediction. A method like Line and SHAP analyze actually the model's behavior to provide retrospective explanation. Their key strength is that they are usable on highly complex model. Okay, but we must be aware that they provide approximation. That means actually can sometimes have errors. Okay, understanding these different approaches allows us to choose the right technique to ensure we can explain our AI's behavior, no matter how simple or complex the model is. Let's now take a deeper dive into one of those categories we just discussed. That means process-oriented reasoning, or in-hoc explanations, or explanation-guided AI. Okay, the core concept behind this approach is something actually, as I mentioned, called process-oriented reasoning. So, what does that mean exactly? It refers to generating explanation by closely examining the step-by-step processes and the intermediate stages that an AI model goes through as it solves a problem or make a decision. This is fundamentally different from explanations that are that only care about the final answer. Instead of just asking why was this specific decision made, okay, process-oriented reasoning helps us understand the entire sequence of action. The logic and also the internal state that led to that specific outcome or decision. As the diagram shows, it's about generating a real-time self-contained reasoning during the model's learning or decision-making processes. The real, power of this approach is that it offers a principled way to build explainability directly into the model without sacrificing the performance. Okay, this is very important. It's also helps in identifying the reducing bias. It achieves this through, it's a typical problem formulation, which you can see in the equation here. Now, without getting lost in the mathematical details, this formula essentially creates a balancing act. It optimizes for two things simultaneously: the accuracy of the model's prediction, okay, and the quality and faithfulness of the explanation. By building, both into the model's objective, we create a system that is designed from the ground up and actually to be both effective and transparent. This brings up
Sorry, can I ask a question now?
Yeah.
So in the previous equation, could you give an example of how the explainability component might look like, or some example of a model?
The main idea, okay, if I want to simply explain, is to you need complementary approaches. Okay, that means we don't have clear or famous approaches for the in-hoc explainability. Okay, the main idea is to use complementary approaches. These complementary approaches, I will show you an example in following this slide, okay? It can be statistical approaches, okay? You can use information theory techniques, you can use Bayesian theory, say, techniques to somehow extract some parameters, okay? And use these parameters to, at the end, help the say training to improve itself automatically. Okay, the main idea is this. The main idea is not just to make only make transparent our AI system, make our AI system transparent, but in addition, we use some approaches to use this explainability to also improve the AI training or learning itself. Okay, this is the main idea. The problem formulation that you see here is completely general. Okay, that means it doesn't give you a, say, clear guideline that exactly how you can apply the say, or have a in-hoc explainability approach. You know, in the following slides, I will explain one of the works that I have done. Okay, just I don't know if it's clear for you, this, or
yeah, I think it's clear for the moment.
yeah, the main
Please,
idea in In-hoc is to actually somehow push or integrate explainability into the essence or nature of AI training, okay, or our deep neural networks, okay. And how we can do this, as I mentioned, you need the complementary approaches, because, for example, Ante-hoc and Post-hoc, for example, for Post-hoc, as I mentioned, we have some tools, some libraries, some techniques. One of, for example, the famous one is SHOP. Okay, SHOP is a very famous explainable AI library that based on the game theory, but provide explainability after training finished. Okay, so but in-hoc explainability, the idea is have a real-time explainability, not after we train the model. So another important in practice, okay, how this can be useful, or how we can use this technique to exactly improve the our AI training and learning. Suppose you understand, okay, how much each feature or input positively or negatively contribute on your output. Okay, in standard AI, you cannot have this information. But if you can have a level of explainability, you can understand how each input or each feature positively or negatively contribute on your decision making or output. When you understand this, you can fine tune your AI model for the next round. Okay, maybe not necessarily involve the feature and input that doesn't have or have negative contribution on your decisions. So it helps you to somehow do an engineering about the feature selections. Okay.
Okay.
It's okay. Let's start and explain what is neural symbolic AI. This is one of another say very hot topic at this time in AI community. This actually brings us to very exciting and powerful approach that directly addresses the challenge of explainability. So what is it exactly? NeuroSymbolic AI is a hybrid approach that, as we say, the name suggests, combines the best of both worlds. Okay, what does it mean? It merges the incredible pattern recognition strength of neural networks with learn from data, okay, with the clarity and structure of symbolic reasoning, which uses logical rules and explicit knowledge, okay. Let's break down it to its to say key components, which you can see in the diagram. First, we have the neural unit. Okay, this is the classic deep learning part of the system. It takes, say, in raw data like images, like text, like sensor, we say readings, and processes it through multiple layers to learn patterns and features. Okay, its output isn't the final answer, but rather an say intermediate representation, say like a set of probabilities or feature embeddings, which is then say passed on. Next, and this is where the actually magic happens. We have the logic units. Okay, this is the symbolic reasoning component. It takes the output. Yeah.
Thanks. This is super interesting. Maybe this is me being a bit simplified, but is this then similar, like a kind of a neural network approach to sort of Bayesian modeling, where you're basically taking like the assumptions and what you already know and then adding the evidence from your data?
Yeah. I will explain you, okay? But if you want, if there is different approaches, again, I will explain in the, say, next slide. It has three main approaches, techniques that how we can apply or have a kind of neurosymbolic AI solutions. But the main, I suppose, somehow integrate human logic into your AI machine, okay? Into your DNN, deep neural networks, okay? Because we don't know what happened inside these deep neural networks that we design, okay? We don't know exactly how they make decisions, okay? Why this fine-tuned this weights in this specific way, okay? How exactly and clearly learn, okay? And another point here is not just is about the explainability, is also is about the safety, okay? That means sometimes in some critical mission application, you need integrate some logics to control the action and predictions, okay? Again, this is another role of the neurosymbolic AI approach. That means beside that, if I want to explain in one sentence, the main idea in neurosymbolic AI is to provide us the decision that is human readable, okay? In one sentence, if I want explain it. So actually, as I mentioned, the magic happens in this symbolic or logical unit. This is the symbolic actually reasoning component. It takes the output from the neural unit and feed it into a logical reasoning, okay, modules. And here it can be, for example, predefined symbolic rules, okay, ontologies or logical constraints that actually comes from an expert, okay, an expert are applied, that this expert can be human. This process say reasons over the neural network's prediction, ensuring the final output is structured, okay, logical, and aligns with established domain knowledge. Okay, most importantly, the output, as I mentioned, is human readable. As the say diagram illustrates, NeuroSymbolic AI essentially, we say, funnel the powerful, say, but often opaque insights from a neural network through a transparent, rules-based framework. This is actually creates a final composite network that is not only highly accurate, but also inherently explainable. Okay, is very important. That means when we design our AI solutions, be inherently explainable. That not just wait after the training, understand that is explainable or not, or maybe during the or into the production, understand this is explainable or not. So now uh, actually that we understand what neurosymbolic AI is, let's explore how it can be implemented. Okay, maybe now your questions exactly are exactly is about this. It's not a single rigid, say, architecture. There are several distinct approaches for combining neural and symbolic components, but each and each say each with its own unique workflow. First, we have learning for reasoning. Okay, as the diagram shows, this is a two-step process. A pattern spotting neural network first takes in raw data and processes it into clean structure, we say tidy fact. Then a separated rule-based engine, okay, or module takes these facts and perform the actual logical thinking or reasoning to arrive at a conclusion. Okay, it's a clean handoff from the learning component to a reasoning component. The second approach is reasoning for learning. Okay, here the roles are somewhat reversed. That means we start with human written rules that act like a safety coach, as I mentioned in previous slide, that it is not just about explainability, it's also about safety and about to be sure that our AI decisions are robust, reliable, and safe. Okay, or a guide for the neural network. These rules actually actively constrains the network while it is learning. Okay, guiding it towards correct outcomes and preventing it from making unsafe or unfair choices or actions or decisions. Okay, the reasoning component essentially supervises the learning process. Finally, we have the most integrated approach. This is the approach that this is my favorite approach, is learning reasoning. Okay, in this model, the neural network and the rule-based system are in, we say, constant dialogue. Okay, they talk back and forth, each improving, we say, the other in continuous feedback loop. The neural network can refine the rules, okay? And the rules can provide stronger signals to guide the network's learning. This creates a dynamic and symbiotic system where both components evolve together. Okay. And yeah, here
Sorry,
just
can you
yeah,
go back to the previous
yeah.
one? So if I were to summarize it, the first one, it's something along the lines of model distillations, meaning that you want to create a simpler model in the form of rules that somehow mimics the decisions provided by more complicated model. And the second approach is something like model regularization, right? Because you can regularize the weights by whatever knowledge you might have about the domain, whether it's some kind of constraints or ontologies, whatever.
Yeah.
Is my understanding correct?
Yeah, the point is, okay, sometimes you have fixed rules when you define rule-based, okay, or your domain knowledge is fixed, not dynamic, not evolve, okay. Sometimes your knowledge base, knowledge domain, or your rule based is evolving, okay, is not fixed. Maybe we can say in reasoning for learning, okay, our rules are more fixed, you know, not evolving. That means, for example, we say, hey, if our deep neural network take these decisions, okay, and has this output based on this rule-based engine or module, it is not safe action, so no trigger it to our environment or systems. Is it clear?
I think so, yes.
Yeah, just let me give you examples, okay? Next slide, and then the slides after that, I will give you example to understand better these concepts. Because first of all, still actually the researchers, engineers, scientists work on these approaches. That means many methods, many solutions in about these approaches is innovative. You know, we don't have standard solutions, and we cannot exactly explain the border between each other, okay. But just maybe the third one, learning reasoning, is more clear. That means somehow the output of neural network is input of our symbolic module, and output of symbolic module is input of our neural network. You know, maybe the third method is more clear. But don't worry, I will explain you with real example and real code, and also explain how you can access them. So now let's bring the concepts together and see how they apply in a, for example, state-of-the-art context. This is exactly your say question. In our work, we focus on applying in-hoc learning reasoning specifically for deep reinforcement learning. Okay, as you know, in standard deep reinforcement learning, an agent learns by interacting with an environment. Okay, to maximize, say, cumulative reward. However, this process faces significant challenges. Okay, rewards can be sparse, meaning the agent only gets feedback at the very, we say, end of a long sequence of actions. They can be also delayed, making it difficult for the agent to credit which specific action led to a good outcome. And sometimes the reward function we design can be non-intuitive, okay? And exactly leading to unexpected or suboptimal behaviors. A common technique to address this is reward shaping, okay? And where we provide additional guidance or additional reward signal to accelerate learning by modifying the reward function in deep reinforcement learning, okay? In our research, we took this a step further. We developed a novel, we say, from of in-hoc learning reasoning that uses a sophisticated type of reward shaping. The goal is to say embed reasoning directly into the agent learning process. But how this say happens, the architecture we propose that you can see here in the slide, it actually is that the details you can have access in our paper that I say put it the title here in the slides. Just let me to explain this a bit. Maybe it helps you to understand better how we can apply in these techniques in real world scenario. So let me walk you through it as the RL agent interact with the environment. Its state is fed into two parallel pathways. Okay, here as you can see, the top path is the standard deep reinforcement learning that here is say graph reinforcement learning and is neural network that processes the states and determines the actions. Okay, that means receive the states from the environment, okay, and take an actions, and we have a reward function that understand the action that is taken based on these states of environment is good or bad. Okay, this is exactly the standard deep reinforcement learning. Crucially, the bottom path, as you can see, actually our symbolic subsystem, this module acts as a real-time reasoner. Okay, how it works? It takes the agent state. Okay, applies logical rules and domain knowledge to it, and generates two important outputs. Okay, here using the Bayesian techniques, as you mentioned. Okay, and actually provide us two important parameters. Is actually measures the importance and explanation. How measure this importance? Actually using the Bayesian techniques to understand how much the connection or relation between different nodes in this design graph are important. Okay, and this measure of importance value comes from this calculation, and based on this say reasoning, it generates an additional explainable AI reward, as you can see. So besides our standard reward function and reward signal that we have, we try to use a symbolic subsystem. Okay, that in this symbolic subsystem we have a reasoner that tell us for example, the node and the features that has the less importance, okay, or higher uncertainty or lower certainty, how should be scored, okay, to somehow filter just and have a more reward for the nodes that have more, say, strong connection with less uncertainty in this graph. And this actually, as I explained, this XAI reward is then used to dynamically shape the main reward from the environment. Somehow we have the reward shaping techniques or reward shaping method. By doing this, we guide the agents, okay, learning process in real time, pushing it toward behaviors that are not only optimal in terms of reward, but also adhere to explicit logical rules and are inherently interpretable. This ensures the agent learns efficiently while producing, say, transparent and trustworthy decision. So here, this symbolic subsystem is completely innovative approach. That means in this symbolic subsystem, you can use other statistical, okay, other mathematical, other, say, theories like information theory, like entropy, to understand or extract some measures that this kind of measures provide you more signal to improve your learning and training. Okay, this is the main idea. I don't know if Is it clear or not? Or
So in this example, what was the task on which you applied this framework? Like,
okay, this is for the main action is, suppose we have a network, okay, and the main idea is to allocate optimal resources to this network. Here is radio resources, can be, for example, computation resources. So we have a network, we have a system, okay, and we have a graph reinforcement learning. And the main idea is to allocate optimal resources to this system or network, okay? But the idea is to somehow make this whole AI training and learning explainable and transparent, okay, and use these extract explainable metrics to improve training itself, okay. That how we say back this, or how we inject or use these explainability metrics by using reward shaping techniques. That means somehow translate this extra signal to somehow reshape our reward function.
okay, makes sense.
This is just a completely innovative approach. Again, we don't have say noun or clear or standard method that we say, hey, this is a well-known method for reasoning learning, you know. Okay, all right, let's move from theory to practice. As Jan mentioned, I have a YouTube channel, okay? In this YouTube channel, I try to share what I learned in the past and what I implemented in different projects, and actually in whole my experiences with the AI community. So you can have access to my YouTube channel, and if you are interested, follow my tutorials there if you find it useful and interesting. The name of my say YouTube channel is BrainOmega. Okay, and here I will explain you one of the tutorial and hands-on that I put in my YouTube channel, and exactly is about how in practice and in reality we can implement this neuro-symbolic approach to AI. And you have also access to complete code in my GitHub page. The link of GitHub repo is in the description of videos. So you can have access both the tutorial, the explanations, and also the link. So here we try to see, or actually propose a reinforcement learning that somehow it equips with neural symbolic approaches, and instead of simple neural network, we use a echo-state network, okay? I will explain a bit what is echo-state network. We're going to say apply the In-hoc learning reasoning principles. We've discussed to one of the classic reinforcement learning problem, the CartPole. Do you know the CartPole environment? Okay, this is one of the famous classical reinforcement learning problem that is it is based on physics rules, okay? And the main idea, as you can see in diagram, the goal is to balance a pole, okay, on a moving cart by deciding whether to say push the cart left or right, okay? That means something like this. The main idea is our AI decisions somehow balance this, okay, not fall down, you know. That means when it's left, try to push it to the right, and when it's right, make it balance and push it to the left to have something like this behavior. Is it clear? Yeah. Our agent, say for this task, is a hybrid, okay, a neurosymbolic system that perfectly illustrated by this split robot. It combines two distinct ways of thinking, okay, just like our human brain. On one side, we have the symbolic module that which we can think of as system 2, our slow, deliberate, logical mind. Okay, this module represents our explicit knowledge and the rules of form we've learned. Okay, for instance, a simple rule, as I explained you, a simple rule would be if the pole is titled far to the left, okay, I should probably push the cart left. Okay, this type of reasoning is transparent and easy to understand, but it can be rigid on its own. On the other side, we have the echo-state network, or ESN. It's a reservoir computing approach. Reservoir computing approach is another state-of-the-art AI approach. Okay, that this ESN acts as our system 1, and it's fast, intuitive, pattern-based part of the brain. Okay, and ESN is a special type of recurrent neural network. Okay, that's excellent at capturing complex flowing patterns from environment over time. So it's a solution that is very good for sequential decisions or actions, or the solutions that is based on the time, like time series. Okay, here it is integrated to policy optimization or reinforce. Reinforce also is a policy based approach in reinforcement learning, and it exactly provides a gut feeling, okay, or quick intuitive response needed for dynamic tasks like this. In this hands-on, you can watch the video to understand how we implemented the architecture. Okay, in the video I exactly step by step explain the code, the different code block, different parts, and you can understand better exactly how it works. But again, we have a symbolic subsystem. Okay, in this symbolic subsystem we used say predefined rules, that these rules can be evolving during the training. Okay, and these rules exactly is a constraint or is an assistant of our neural network or our echo state network. Is exactly what we explained in previous slides. So I think also explained this. And yeah, let's start the alignment concept. We have a limited time, no? Okay. Just I try to be more quick. As we move into the world of large language models or LLMs, a critical concept we must understand is alignment. Actually, in previous AI hostel world AI sessions, Jan explained about ethical AI. Okay, this is exactly related to this kind the concepts of alignment. So what is alignment? In simple terms, it's the entire process of designing and training and a large language LLM to ensure its behaviors and goals are directly in line with human values and intentions. It, we say, the work that goes into making sure an AI is a safe, cooperative, and useful tool for people to use. Okay, this process generally focus on three core pillars. First, the model must be helpful. What does mean this? This means it should correctly interpret what the user is asking for and do its best to fulfill that request successfully. Okay. Second, it must be honest. This is, say, crucial. The LLM provide information that is say factually accurate and avoid fabricating facts. No, part of being honest is also admitting when it doesn't know the answer. That means when you ask a question, okay, or ask something from your LLM, it's important, if it doesn't know the answer, tell you, hey, I don't know the answer of this question. Okay, so this is related to the honest. And the third, it must be harmless. This model is explicitly trained to recognize and refuse to generate dangerous, unethical or harmful content. Alignment is a framework we use to guide these incredibly, say, powerful models, ensuring they work for us. Okay, this is very important, and with us, safely and effectively. And this leads us to a very important question. Okay, if we succeed in aligning an LLM, does that automatically make it trustworthy and explainable? The answer is, say, nuanced. Let's first consider trustworthiness. This link here is very strong. Okay, we trust systems that are reliable, predictable, and act with our best interest in mind. Since alignment is the very, say, process of instilling these qualities, okay, helpfulness, honestly, and harmlessness. A well-aligned LLM is, by its nature, a more trustworthy one. Okay, the more aligned it is, the more we can depend on its outputs. Now let's look at explainability. This is where the connection is much weaker. Okay, as we discussed earlier, explainability is about understanding the why behind a decisions. Alignment, however, it's primarily concerned with, say, the what, the final output. And LLM can be perfectly aligned to give you a safe and accurate answer, but we still may not be able to trace the complex, say, pathway through its billions of parameters that lead to that specific sequence of word or answer. That means the internal process remains a black box. Okay, even with alignment, our LLM models still is not fully or completely explainable. So to conclude, alignment is a fundamental, essential component for building trustworthy large language models. Okay, however, it is not a substitute for explainable AI. Achieving true explainability in these massive, complex models remains exactly a separate and very active area of research. And just let's break. I don't know, my time is finished, but if it's possible, give me 5 minutes more, if no problem.
Yeah, I can do 5 more minutes.
Yeah, just very quickly. Let's break down the foundational algorithm for large language model alignment. The most famous one that, for example, you can see in GPT in OpenAI, okay, is reinforcement learning from human feedback, or RLHF. Your understanding of it was spot on. So let's walk through that and say precisely explain the 3 different steps that it has. First is supervised fine-tuning, or SFT. We begin with say general pre-trained model and fine-tune it on a say a curated set of high quality human return examples. Suppose we have a data set, okay? In this data set, exactly consist of some questions and some answers, okay? But maybe only one answer is correct and the other answer is not correct, okay? The data set has this kind of structure. This initial step is say critical for teaching the model the desired say conversational style, tone, and basic safely principles, creating say strong starting point. After that, we have the second step, that means training the reward model. We use our SFT, or supervised fine-tuning model, to generate several different responses to a variety of prompts, okay? And then human reviews ranks of these responses, okay, creating a rich data set of human preferences. And this data is to train a separate reward model, okay, whose sole purpose is to learn to predict which outputs a human and would prefer. And finally, we have reinforcement learning optimization stage. The SFT model, we say, now act as our reinforcement learning policy. For any given prompt, okay, it generate a response, and the reward model we just built score that response, okay, and that score becomes say the reward signal. Using a sophisticated algorithm like proximal policy optimization, or PPO, we update the model to maximize this reward, exactly what we have in standard deep reinforcement learning approaches. And here's a crucial details. We use, for example, a KL penalty, okay, as a safety rail. The callback Libler divergence is a way to measure how different that here is two probability distributions are, okay? In the context of RLHF, we use it to keep our updated model from drifting too far away from the behavior it learned during supervised fine-tuning. And this penalty ensures that the model optimizes the higher rewards. It doesn't say drift too far from the coherent and sensible language distribution it learns in the SFT stage. Actually it prevents the model from actually finding odd loopholes, and ensures the final output remain high quality. So together, these robust steps effectively align the model's behavior with complex human preferences. If you are using with ChatGPT or Gemini, you have an option after they provide you response, tell you, for example, do you like it or not? Okay, and based on these likes, based on what you provide sometimes as a comment, for example, maybe provide some context you find it is not legal, okay, you have this option to report this kind of responses, and the model, specifically for the like and unlike, the model can understand how much the quality of the answer that provide you is high or is low. So, and my last slide, where does the where does the field of alignment go from here? Okay, this is also important. While it is important, because RLHF is very complex solution, is a resource hungry solution. Okay, and already researchers are experimenting with the next wave of techniques, okay, that needs, for example, less complexity, has or more has say more speed, and is more efficient. This include using we say AI to automate preference labeling, which could dramatically speed up the creation of training data. It includes also constitutional AI method solution we just discussed, and which bake high level principles directly into the models. And it actually involves creating more sophisticated training curricula designed for that, say, specific domains. But what's crucial to understand is that whatever new twist emerge, okay, the fundamental philosophy of alignment will likely remain the same. Okay, it's about the channeling human values into this system through a real, robust, clear, and intuitive progression. So first we lead by we can I'm talking about new approaches. We can lead by example. This is the supervised fine-tuning phase, showing the model what good looks like. Next we deepen into understanding by preferences. Okay, this is say reward modeling phase. There the model learns say the nonce of what we prefer, and finally the model continuously refines its behavior by feedback. Okay, this feedback is very important because this feedback somehow comes from expert or comes from human, and it can have say very important role to somehow improve this large language model performance and alignment. And that, yeah, that's it. Sorry.